Hello and welcome to this lecture. We've seen the definition of the limit. We've seen when the limit exists and it's finite, etc. And then we saw this epsilon definition, and we saw several examples where the limit was finite. There were examples where the sequence was diverging off to plus infinity, diverging to minus infinity. I want to warn you that in many, these terminologies are slightly different in various places. Some people will say it is converging to plus infinity, converging to minus infinity, while they'll say the divergent is basically means limit does not exist. But I prefer to use this terminology because I think infinity, I don't want to think of it as the same thing as a finite number. So we'll say in this class, when I say converges, I mean converges to some finite value. If it goes off to plus infinity or minus infinity, I will think of it as a divergent behavior. It is diverging to plus infinity, diverging to minus infinity. And there can also be cases where there is really no limit at all. None of these three things happen. Okay, so some convention we are using in this class. We'll keep that going. Okay, so now that we know a few limits, we know the constant limit, we know the 1 by n equal to 0. It turns out you can use this to compute more and more limits. Okay, so in this lecture we're going to see how to do that. Okay, so for doing that you need some rules. Okay, but before we go into that rules, a lot of people ask, why should I know how to compute limits? What am I going to do with knowing limits? What has it got to do with engineering? I'm making an electronic system with my hands here. I have to know what to do. Why are you teaching me limits? The point is, the parameters and variables you have in your engineering system, let's say a voltage in an electronic circuit, uh, it varies with time. And even if you're doing digital processing, the samples vary with time as you process. And in some cases, the samples may converge to some finite value. Like for instance, in this case here, it is sort of converging to a finite value. In some cases, it may increase and fall down to 0. In some cases, it may sort of oscillate, but then the amplitude will decrease and go to 0. But notice here the dangers of what is happening here. Here also it's oscillating, but then the amplitude is blowing up, blowing up, blowing up. And this can happen. Or the amplitude may stay the same. It may do a nice sinusoidal thing. All of these things happen in electronic circuits. And some of these things are okay. Some of these things are not okay. For instance, the blowing up scenario is clearly not okay. Nothing you can do after this. And all of these things are limiting behaviors. What happens in the limit? What happens when a long time has elapsed? How do you study these things? So, of course, you can build electronic systems without knowing these things, but then some instability will happen. It won't work, or something will go wrong, and you wouldn't have built a good engineering system. If you want to build a good engineering systems, you want to be a good engineer, you better know your limits. You know how a signal's equation has to be written as a function of time, and you have to know how that could be a sequence, and that could how it behaves for large values of time. And all of that is very, very important. So keep yourself motivated by knowing that these things have applications, are extremely good, clear applications. And if you know this, you'll be a much better engineer than not knowing these things. Okay, so what are these rules? There are rules for combining limits and then creating more and more limits, solving more and more limit problems. The rules are actually very, very simple. So it turns out, okay, so what do we know? We know these two limits, right? So these two limits we know. Limit of a constant sequence is itself, right? If the same thing is repeating over and over again, that is the limit. I technically didn't prove it for you, but it's quite simple. I think you'll agree with me. And we actually saw the proof for why limit as n tending to infinity of 1 by n equals 0. So these are the two limits we know. Just with these things, what else can we do, right? So if we've been using this principle in this course all the time, you start with some simple basic relationships of facts, and then you use some logic to create bigger and bigger facts, bigger and bigger results and all that. So we're going to do the same thing here. Like I said, we'll keep repeating the same thing throughout this class. But here we need some logic. Okay, so this I'm going to give you a bunch of logic for why these things should work. I won't strictly prove it for you or something. One could write a proof. It's not very hard using the epsilon definition, but I'm not writing a proof. But I'll give you the logic, and we'll use that logic throughout. Okay. So for this to work, you have to generally suppose that an and bn are convergent sequences, as in their limit exists and they are finite. Okay. So this is good because then I don't have to present all exception scenarios, but later on we'll relax at least what happens if for one sequence diverges to infinity, how do we combine, etc. We'll see that a little bit later, but let's assume for now that both these sequences have limits and they are finite, an and bn, two sequences. So what happens if you scale a sequence? What happens if you add two sequences? What happens if you subtract two sequences? So these are the combinations, right? Maybe I know the limit for an and bn. Now, instead of asking the question, so now not instead, now I'm going to ask the question for what happens to a constant multiplied by an. What happens to that sequence? Does it have a limit? Okay. And if yes, what is the limit? So likewise for an plus bn. If I know an's limit exists, bn's limit exists, if I add the two sequences, then ask for the limit, what happens to the limit? Okay. So all these things have very simple rules. So these are the three rules here. I've written this down and you'll probably easily believe me. And it's possible to prove these things rigorously, as in you use the definition of the limit on these sequences and the fact that each of these things converge. You can imagine graphically in your mind, right? An is sort of converging to, one sequence. Everything is within an for a large enough n. Bn is also converging to some other limit. Everything after a particular n is, very close to Bn. So now an and bn, even though they are sequences, after a certain point, they're going to be close to their limits. So even if I add or scale or subtract, I should be able to subtract the limits. Okay, it should just work. I mean, you can imagine this graphically. I've not drawn that slide for you. You can draw it for yourself. You can see that even if you add the sequences, because each of the sequences are going around a particular finite value, whether you add them or subtract them or scale them, the limits should also correspondingly change. Okay. So that's an easy enough thing to see. I'm not writing down or proving it. Imagine this graphically and you'll see what's happening. Okay. The same thing interestingly holds for a few other slightly non-trivial operations. One is multiplication. Okay. You take the sequence a and bn and multiply it together. Again, the limit, you can take the limit inside the multiplication. You take the limit of an like the limit of bn, multiply the limits, you get this. Okay. This needs some additional proving, but you can imagine why this should be true. Like I said, an by itself is coming close to that limit, bn by itself is coming close to its limit. So when you multiply also, this should be okay. Okay, so this needs technically some proof. I'm skipping that. This works. Same thing happens if you take a sequence and raise it to some power. Okay, see, multiplication, repeated multiplication is an par k, right? Once you know an bn is like this, instead of bn, if I put an itself, I know that an squared will follow this rule, and then an cubed will also follow this rule, right? I put an squared times an. You can repeatedly use it and show that this is true. So this is okay. This is all right. And if you look at this guy, an by bn, this needs some careful proving as well, but this is also true. Division also is true. You take two sequences, and as long as the limit of bn is non-zero, you can take the limits inside the quotient. Okay, an by bn, it can be limit in the numerator, limit in the denominator. Okay, so these are powerful rules, very simple rules, and this will help us move from limits that we know to newer and newer limits. So now I'll start combining sequences, just constant and 1 by n. I'll start combining. I'll show you how they look soon. And then for those new combined sequences, because I know the limit for constant and 1 by n, I can use these rules and find the limit. Okay, I just need these kind of conditions to hold true. Okay, I have not proven these things. There are proofs in many places. You can look it up, but using the epsilon definition, you can prove all these things. The scaling, addition, subtraction is probably very intuitive and clear. Multiplication and division, slightly more complicated, but it turns out the limits are okay in this fashion. Okay, so these are important, and this we are going to now use and increase our collection of limits that we know. What all can we do? Okay, let's see a whole bunch of examples. I have some 9 different sequences here, and all of them are quite easy to do. Look at the first one, 2 plus 3 by n. Okay, notice what's happened here, 2 plus 3 by n. Let me just do this in the notes here. The first problem, an is 2 plus 3 by n. Okay, so now what is going on here? There are you can write it in so many different ways, right? There is a sequence 1 by n whose limit we know. Okay, I am writing it laboriously. I mean, as you become more and more comfortable with limits, you will just look at this problem and you will know the answer, right? So it will go quickly for you, but first time you are doing it, you have to sort of do the decomposition yourself. And then what's going on here? I have done 3 by n. What about 3 by n? Limit as this is known limit. Limit as n tending to infinity of 3 by n is 3 times limit as n tending to infinity of 1 by n. So what rule did I use here? Scaling. Okay, I have taken a sequence 1 by n, I have scaled it by a constant 3. Okay, and I know my limit goes inside the scale, so this is true. So this is 3 times 0, which is 0, right? Now I know this. So this I have done. And then what can I do here? There is also one more limit I know. Limit as n tending to infinity of 2 is just 2. And here I have summation, right? So here I have just summation. So using all of these guys, you see the limit as n tending to infinity 2 plus 3 by n, using the sum rule is limit as n tending to infinity of 2 plus limit as n tending to infinity of 3 by n, which is just 2 plus 0, and it's just 2. Okay. So I have written it laboriously, telling you all the laws, etc., but you can see easily how these things are done, right? So basically, limit distributes itself over addition, multiplication, and division. Okay, that's the way to think of it from a high level. Limit will distribute itself, as in you take limits, it will go in, right? If you have limit of two sums, 2 and 3 by n, you can do limit for 2 separately, 3 by n separately, and then add the limits. You get the overall limit correctly. And in 3 by n also, you take the 3 out and take the limit in. Okay, so this is how you have to sort of algebraically, operationally think about this limit taking for a bigger expression. So you have 2 plus 3 by n, which is a bigger expression. I am taking limits on that, and the limits can go inside. You think of limit as an operation. It's very important. Taking limits of an expression. So this is a common usage that you'll see. I am taking limits, I get this. So I took limits for 2 plus 3 by n, and I got 2, right? So if and here when you take limits, you can distribute. Okay, limit distributes over plus, minus, multiplication, division, all of those operations. Limits, as long as it's finite and easy, there's no problem. You can happily distribute it and then do the computation, you'll get the answer. Okay, so I've shown it laboriously here. In future problems, you'll see I will just take limits and I will do the distribution. I will not go over every step and write scaling, sum and all that. I'll just quickly say, okay, I'm taking limits, limit goes into the numerator, limit goes into the denominator, limit splits over addition, limit splits over minus. All of that I will sort of implicitly do and do it very quickly. The logic we're using is exactly the same. So let's attack the second problem that way. Okay, so let's attack the second problem. But the second problem is a little bit, I'll ask you to be a bit cautious there. You'll use an idea that is slightly different. The sequence is defined as 2n plus 5 by 3. 2n plus 5 plus 3n. Okay. If you stare at this problem immediately, you're a little confused, as in saying, what do we do here? There is no finite limit, right? If you think of distributing the limit, okay, so you take limit to the numerator and limit to the denominator, you see that limit as n tending to infinity of 2n, this is diverges to, this one diverges to plus infinity, right? So the way we write it as infinity. Okay, so this diverges. So now my limit distribution does not work, right? If I want to distribute the limit and if it becomes infinity, not that it does not work, we haven't yet seen it. We've seen limit distribution only for finite limits, right? So how do you convert this into finite? Okay. So here is where a trick comes for rational functions. Rational, this is meaning there is a numerator, there is a denominator. I have this problem of I'm having these limits diverging off to infinity, I'm not able to use the distribution correctly, right? So what you can do is, here is a important trick, this is a very important trick and you should keep this in mind. Divide numerator and denominator by n. Okay, so this is a crucial idea. And you're allowed to do it. I mean, you just divide both numerator and denominator by n. Of course, you can do it. So you get 2 by 5 by n plus 3. So both of these expressions are exactly the same. They're not different at all. But look at what has happened dramatically. If I now take limits, okay, I will see that limit as n tending to infinity a n is, I know my limit can distribute, right? So let me also write, this is like early days, so let me write the steps in detail for you, right? I have a numerator and denominator division, limit distributes over division, right? So it's going to be limit as n tending to infinity of 2 divided by limit as n tending to infinity of 5 by n plus 3. Now I don't have any problems. Okay, so the way you do it is you assume distribution works and you distribute the limit, but anytime you have an infinity or anytime you have a problem, you have to just stop. I mean, some step is wrong if something goes to infinity. Okay, but here we are not going to infinity, everything is finite, so you're okay, right? As long as everything is finite, things are good, because that's only then the distribution of limit so far works. We will deal with the infinity case soon, but that is a little bit more complicated, so we'll do that separately. Okay. So now I'm in very comfortable zone, right? What is limit as this guy going to 2? That's 2. 3 plus 5 by n, we saw a variation of this, so it's just 2 by 3. Okay, so you see how again limit will distribute over addition, limit of 5 by n, then the scaling 5 comes out, then that's 0, then you have 3. I'm not writing all those steps, hopefully you see that. So it becomes 2 by 3 finally. Okay, so this is like taking limits on an expression and using our wonderful combining rules for limits, finite limits, we're able to very easily do it. And notice this trick here, I went from these infinite limit problem to the finite limit case just by dividing numerator denominator by n. This is a very powerful trick to convert problems that don't fall into our bucket of finite limits into finite. Okay, this is problem 2. Let's see problem 3. 3 is probably also equally nice. It's 2 plus 5 by 3n. Hope I got that right. 2 plus 5 by 3n, yeah. So here the distribution is very easy, right? The numerator, but can you do that? Can you go into the numerator immediately? So numerator seems fine, but denominator, when you go and take limits, you'll see you'll run into problems. So let's just assume the distribution works and go and do it. Limit as n tending to infinity 5 plus 3n. So here you have a problem. Okay. So what do you do? So you shouldn't proceed like this. You should do divide numerator and denominator by n. Notice that this dividing by n suddenly makes things wonderful for you. You have 2 by n, 5 by n plus 3. Okay. So things have changed now. So now you identify the numerator has a finite limit of 0, denominator has a finite limit of 0 plus 3, denominator is non-zero. So all of those things are fine and you can just use your limit argument now. You can see limit as n tending to infinity of 2 plus 5 by 3n is simply 0 by 3 and it just becomes 0 plus 3. Okay, so you see once you come into a form that's nice for you, everything works out fine. So once again, when you take limits, denominator should be non-zero finite number, numerator should be finite. As long as you do that, everything is fine, you can carry on. Okay, if you have infinity, just watch out, see if this dividing numerator and denominator by something will help out and all that. Okay, so that's problem 3 for you. Let's go to problem 4. Ooh, it seems to have n squared and all. Let's see what happens there. N squared plus 2n plus 4 by 2n squared plus 3. So let's do that. You get it right, 2n plus 4 by 2n squared plus 3. Okay. So how people do this is basically, you notice already that there is a problem if you directly apply your limits to the numerator and denominator, because things are blowing off to infinity. And you need some division. We can see if division trick will work. But then if you divide by n, it's not going to work. If you divide by n, you still have a n in the numerator and n in the denominator, right? So if you divide by n, what happens? If you look at 2n squared plus 3 divided by n, I'm going to get 2n plus 3 by n. Okay, this part is okay, but then this is still infinity, right? So dividing by n is not good. So what do you divide by? You notice that there is n squared going on here. So maybe you want to divide by n squared. So if you divide by n squared, you see that things will go finite for you. Okay, notice everything now has gone finite, and now you can push your limits inside the numerator and denominator and simply get the answer of 1 by 2. So notice how easy it is. If you just remember the rules and use them correctly, logically, things work out very, very smoothly. And you just this trick of dividing the numerator and denominator in fractional expressions to get to a finite limit form is something that's very, very nice. Okay. A lot of other ways in which people interpret these things. Maybe later on we'll see that when we get a chance. Okay, that's 4 for you. I'm going to skip 5. Okay, 5 is very similar to 4. Once again, you'll have to divide by n squared, and the answer I think will be 0. You can check that out. This limit will be 0. Let's do 6. 6 is a little bit slightly more interesting looking problem. 1 by n minus 1 by n plus 1. There are various ways in which you can do this. You can take the limit inside the subtraction. So you can see that this will be limit as n tending to infinity 1 by n minus limit as n tending to infinity 1 by n plus 1. Whenever you do this distribution, you have to keep watching out. If you get some infinity somewhere, you have to pause. It's gone wrong, go back and redo it. But here you won't get any infinity, because see, this limit as n tending to infinity of 1 by n is 0. This one is also 0. Okay, 1 by n plus 1. You can quickly check. If you want, you can divide by n numerator, denominator, do such stuff, and you get it. Otherwise, also 1 by n plus 1. You see that the limit will be 0. You'll get 0. So some people like to also simplify this. You can simplify this as this is actually equal to 1 by n into n plus 1, right? So if you take the denominator common, n into n plus 1, then you'll get n plus 1 minus 1 1 by n, which is 1 by n squared plus n, and then you divide by n squared. You can do like this also. Okay, you divide numerator and denominator by n squared, you'll get 1 by n squared plus 1 by n, and that will be again 0. So you'll get 0 here. Multiple ways to do this problem. Okay, just watch out. There were no infinities, so we were okay. But we have to be very careful. If you hit some infinity somewhere, then you'll have to backtrack a bit or divide numerator, denominator, things like that. You'll have to do. Okay, so 7, 8, and 9 is just thrown in there to show you large sized numbers. So this can happen, and sometimes people get a little confused as to what will happen here. Wow, 10 power 26, maybe the limit is something else like that. I just wanted to tell you what happens here. I'm not going to do it in detail. You can see what will happen. So however large the scaling constant is, this is just a scaling, right? So it looks like the scaling constant is 10 power 26, but remember 10 power 26 is just a finite number. When I say limit as n tending to infinity, I am making n could be much larger than 10 power 26. Okay, so here the limit is actually 0. Okay, you're right. I think till n becomes even 10 power 26, the sequence is just 1. It's not even showing any tendency to tend to 0. But as n becomes larger and larger, even larger than 10 power 26, however large the scaling is, eventually the sequence will go to 0. Okay, so such sequences show you both the power of limits and the limitations of the limiting operation. Right? So when you have large constants like these in your expressions, the limit, though it gives you a valid answer, when n becomes really large, it does tend to 0. That's correct. But in practice, the sequence may be finite for a long time. So that just depends on the constant. Okay. So watch out for these big constants in these expressions. So if there are big constants in these expressions, in engineering problems, you may run into trouble. So even though limiting wise you're okay, the limit will only apply for such large values of n, and in your engineering problem it may not be very relevant. Okay, so these are things to watch out for, the pitfalls of limits in practice, but also in theory. In theory it works, there's nothing wrong with that, but practice these things may hurt you. The next problem also has something like that. So n by 50,000 plus n. Okay. So any small value of n you put, it looks like this is a very, very small number, but interestingly, what is the limit? If you actually compute the limit, you will get 1. Okay. Get 1. Think about it. So you have to divide numerator and denominator by n. So you'll get 1 by 50,000 by n plus 1. And that 50,000 by n will scale whatever, however big the scaling is, the limit is 0, right. So you get 1. So this will eventually become 1, but only when n becomes really, really large, much larger than 50,000. Okay. So only when n is much, much larger than 50,000 does this really go to 1. Okay. But when n is small, this is still a large fraction, small fraction. Okay. So keep that in mind. So what am I pointing out here in these kind of examples? Depending on the constants you have, you may have to go to really, really large n before the limiting behavior kicks in. Okay. So something to watch out for in your expressions. If you have an expression in an engineering system and it's got these large constants, the limit you have to be a little worried about. Okay. Same thing here, the ninth problem has this 10 power 6 sitting here. So for any small value of n, this 10 power 6 will sort of dominate. Okay. So this is the way people think about it in expressions, right? How to assess the behavior of something. They'll look at the denominator and they'll say when n is small, this 10 power 6 is going to dominate. So this denominator is like 10 power 6, the numerator is something minus. So it will be very small. But n becomes really, really, really large, right? When n goes really large, the 7n is going to be so large that 10 power 6 becomes small, right? Maybe n is 10 to the power 200, right? So compared to 10 to the power 200, 10 power 6 is nothing, right, in the limit. So this denominator is just like 7n. Likewise here 1 minus 3n, when n is like 10 power 200, this 1 is useless, right? So 3n is what you want, so this will go to minus 3 by 7, okay. So these are ways in which people read expressions and limiting values just by looking at them and using in their minds this, what happens to the limiting behavior. So what will happen for large n, what will happen for medium n, what will happen for very small n. All these things are limiting evaluations, and as an engineer, being able to look at an expression like this and sort of quickly, roughly compute the limiting behavior, or exactly compute the limit for asymptotically large n, is an extremely valuable trick. And in a system, you will know how things behave if you can do limiting behavior in a nice way. Okay, so hopefully this showed you how to combine simple limits. This is a very, very important thing. And in your exercises and assignments, you will see more such examples for getting practice for this. Okay, thank you very much.